In this question, a uniform cube of side B and mass m rests on a rough horizontal table. A force F is applied normal to one of the faces at a point at a height 3b/4 above the base. What should be the coefficient of friction between the cube and the table so that it will tip about an edge before it will start slipping? Dear student, there will be a downward gravitational pull as well, mg, at the center. Now since it is a cube, the horizontal width is also b. There will be an upward normal force n, and there will be a frictional force F here. Now dear student, for it to topple, the torque should be just 0 or just about to cross 0, then it will be in a case of just toppling. Now balancing the torque about point A, we can write down that F into 3b/4 minus mg into b/2 should be greater than or equal to 0, which means that F should be greater than or equal to 2mg/3. Now for no slipping, this F should be less than the maximum value of frictional force. That means that 2mg/3 should be less than or equal to mu mg, or mu should be greater than or equal to 2/3. And hence for this question the correct answer turns out to be option number 1. Now let us solve the question number 42. In question 42, a disc of radius r is rolling purely on a flat horizontal surface with a constant angular velocity. The angle between the velocity and the acceleration vectors of point P is something that we have to calculate. Now dear student, the velocity here will be due to two components, that is omega r, which will be equal to v, and a rightward v as well due to the center of mass. So the net velocity will be in 45-degree angles direction and the magnitude will be root 2v. Now the acceleration vector will be in the rightward direction towards the center and will having a value of omega square r. And hence we can clearly see the angle between the velocity vector and the acceleration is 45 degree, and therefore for this question the correct answer is option number 2. Now let us proceed and solve the question number 43. In this question, 2 points of a rigid body are moving as shown. The angular velocity of the body is something that we have to calculate. Dear student, the angular velocity can be easily calculated by using the formula that will be velocity divided by the distance from the center. So this will be v/r, and hence straight away the angular velocity for this particular body will be v/r, meaning that the correct answer for this question is option 2. Moving on to the question number 44. In this question, two particles of mass 2 kg and 6 kg are moving on a smooth horizontal surface. They collide with each other. The velocity of the common center of mass is 10 meters per second before collision. Then what is the total linear momentum of this system of particles after collision? Assume that they move along the surface after collision. Dear students, the velocity of the center of mass remains unchanged in the collision. So the final velocity of center of mass will be again 10 meters per second. The total linear momentum will be simply total mass multiplied by the velocity of center of mass. So this will be 2 plus 6 into 10, that is 80 kg meter per second. And hence for this question the correct answer is option number 3. Moving on to the question number 45. In this question, a ring of mass m and radius r rolls purely on a horizontal surface under the effect of force F as shown in the figure. The average power delivered by the frictional force on the ring in time t will be. The students, it is given that the ring rolls purely. So therefore, there is no skidding at the bottommost point. The point of contact with the ground does not move with respect to the ground. And hence, the power, which is simply force multiplied by velocity, will be 0 due to the reason that the velocity of the point of contact is 0. Meaning that the correct answer for this question is option number 4. Dear student, this concludes the discussion of the quick solutions of this AIATS for the OIM batch, that is test number 6. I hope you understood all the solutions. I thank you very much for watching and wish you all the best for your future endeavors. God bless you all.